Differentiation, part 2. All right, we have learned about differentiation rule. And next, we are going to learn about optimization of y with one independent variable. One independent variable. Okay, and next is to learn also about optimization of y with two independent variables x, z. Two independent variable. Okay, so we are going to do the number 2. So what is actually optimization with one independent variable? It is the things like you have learned before the midterm exam. Yeah, we have learned about the quadrat function, and the quadrat function is can be like this or the other way around like that. Yeah, so the main thing is that we want to find the maximum and minimum point, or the stationary point here. Yeah, so this is what we call it optimization. So next will be that it's no longer quadrat function, but it can be like this, right? So we need to find all of the peaks over here. Yeah, so we can see here that this is a maximum. There are 3 maximum points here. We can call this one as an extreme maximum, and this is the local maximum. And we also have here the minimum point, also here minimum point. This is the extreme one. And what other things here is that this is also some kind of stationary point, but we say that as an inflection point. Why? Because it is going down right over here. Yeah, it's going down like this, and it stop, and it's go down again. So this is what we call with inflection point. Inflection point. So the goal mainly here is to draw the function. Remember what I have said in the class, that from all of the things that we have learned here, the end of the the output here, the last output that we need here is to visualize all of the things that we have worked on. Okay, so we need to visualize all these things into a graph, because people want to prefer to see the graph rather than seeing the data or the numbers. Okay, so that's why it is very important to draw that. And instead of drawing all the points, we just can find that only through the all the stationary point here, the important one, and then just draw that. Okay, right. So now we go to how to draw that if the function is depend on one independent variable. So first of all is that we need to find the stationary points through the first derivative, right? Then set, oh sorry, it should be still 1. I think I forgot to erase this. It's still belong to number 1. Okay, so find the stationary points through the first derivative dy dx, and after we find the first derivative, then we set that dy dx as 0. After that, we will find the x stationary point and also y stationary point. Yeah, it can be more than one though. And then after we find this stationary point, then we need to test that whether that point is a maximum point or minimum point or inflection point. So how to do that? By finding first the second derivative. Okay, after we find the function of second derivative, then we need to substitute the x stationary point here into the second derivative function. So if the value of that positive or bigger than 0, the curve is concave upward. Remember, if it is positive, then you're smiling. Yeah, so the point is a minimum. And if it is negative, the point is maximum. And if it is 0, the point will be called with inflection point. So we don't know whether it is going down or going up. Going down or going up. Oh, excuse. Going up. So this is the inflection point here. How we check these things out? It's through testing that into the original function. Yeah, with the coordinate of x on the left and the right of the x stationary point. Then the third one is to draw that. Okay, well, I will explain that through the example next. Okay, so we have an example here. I'll pick these exercises from the Kalang's book. This is from chapter 14, all of them, yeah, chapter 14, and this is from 14.2 example, and 14.5, the same, yeah, and this one is 14.6, if I'm not mistaken. You can check that again into your books. Okay, right, so I will explain about number 1. Okay, let's start by following the rules that I have mentioned before. Let's divide it first, the screen. Okay. So what we need to do first is to we will find the stationary points. Okay, so we have here the highest power is 3, so the stationary points maximum will be 2. Yeah. Okay, so if you later on you made another function like power like 4, then the maximum stationary points will be 3, so just subtract that with 1. The maximum, yeah, it can be less, but it cannot be more than that. All right, now first of all, define the first derivative of y. Okay, dy dx is 3x 3 minus 1 minus 9 times 2x 2 minus 1 plus 15. Okay, so that will be 3x squared minus 18x plus 15. Then set dy dx equal with 0. Now again change this, 3x squared minus 18x plus 15 is 0. Now you see here that it has a factor of 3, all of the numbers here, so we can divide it directly with 3. and it become x squared minus 6x plus 5 equal with 0. Factorize that. If you still not good at factorization, then just do it ABC formula. Okay, see the left, x squared is x times x, plus 5 can be plus 5 times 1, or minus 1 minus 5. Again, see in the middle here, it's minus 6, so 1 plus 5 is 6, then it should be minus here, so then it will become minus 6x. Okay, now this is x minus 1 equal with 0, and then x minus 5 equal with 0. So we have 2x stationary point, x1 is 1, and x2 is 5. Now, the y1 will be, substitute x1 to the original function y, and that is 1 power 3 minus 9, 1 quadrat plus 15 times 1 plus 35, and that will be 42. Okay, for y2, x2 is 5 to y, 5 3 minus 9 times 5 quadrat plus 15 times 5 plus 35. Okay, 125 minus, well, it's 10, I think. Yeah, it's 10. So the stationary point, there are two stationary points, and that is 142 and 5 10. Okay, so now we have to, the second one is, we don't know yet what kind of value that the stationary point has. Is it maximum, minimum, or inflection point? So now test the optimization, the stationary point, I mean, points. Okay, through what? Second derivative of y. So now d quadrat y dx quadrat. Okay, let's see. We derived that through the first derivative here. It is, yeah, 3x quadrat, derive that, 3 times 2x, power 2 minus 1, right? And then minus 18. So then it becomes 6x minus 18. So this is the second derivative. And then check it, yeah? Check the x stationary one. X1 d quadrat y dx quadrat equal with, check 6 times 1 minus 18, it is negative, right? Minus 12. So this is smaller than 0. It means it gives a maximum value. So this is a maximum point. The curve is going downward. Okay, and the second one, x2 5. So d quadrat y dx quadrat will be 6 times 5 minus 18, that is 12 positive, and so this is a minimum point. Okay, so 142 is a maximum point, and then 510 is a minimum point. Okay, now draw The third step is to draw. Remember, use your ruler, yeah. So this is 1 2 3 4 5 1 2 3 4 5 here. So the step here is 10 for the y, yeah. 10 20 30 40 50. So this is a 40, and for the axis, x-axis is one step here. Okay, so now 142, it will be here. Okay, here is the 42 more or less, yeah. And then 510 is around here. Now, so this is things goes like this, yeah. Okay, now pull all the line and it goes here. If you want to be sure on where this line will goes to intersect the x-axis, so you can check using if it is intersects the y-axis, it means that you can give x equal with 0, and then find the coordinate of the intersection then. So that is x times 303 minus what's that again, minus 9 times 0, it's also 0 quadrat plus 15, 0 plus 35, so this will be 35. So more or less is here. Now is your drawing, it's more subtle. Okay, so this is how you make the optimization of this function. Okay, now we go to the second example. Yeah, this is a kind of not a kind of, but this is an example of how you when you will meet in an inflection point function. Okay, so okay, now we go again to the stationary point. Find the stationary point. Okay, yeah, I'll shorten it because well, I have a lot to write here, so for you need to extend the what S and P means. Yeah, stationary point. Okay, first of all, find the first derivative of y, of y, dy dx is 1/3 times 3x 3 minus 2 minus 5 times 2 x 2 minus 1 plus 25. Right? 1/3 times 3 is 1. 1 times x is x. And 3 minus 2 is 1. So leave it. Sorry. This should be 1, yeah. So this is a quadrat. And here is 10x plus 25. Now set dy dx equal with 0. X quadrat minus 10x plus 25 is 0. And here is the factors of that. X and x plus 25 is 5 5, because it is mean, then I think this is mean. So you see here that this has a this is the same as x minus 5 quadrat. So the solution of this only one, yeah, x minus 5 only, so x5. So you see here that I've said before that for the function with the highest exponential 3, it will the maximum stationary points will be 2. It can be less than that, but it cannot be more than 2. Okay, so this is the proof that it can be less than 2. Right. Now oh, I haven't find the y. Yeah, okay, so here substitute x of 5 to y to the original function, then y will be 1/3 times 5 3 minus 5 5 quadrat plus 25 times 5 plus 10. So this can be dismissed, and that will be 51.67. Okay, so the stationary point is, okay, I'll write here, the stationary point will be 551.67. Now we will check that through the second derivative. Okay, we'll check the second derivative here. Check the stationary point, define the second derivative. Okay, d quadrat y dx quadrat is, start from here, 2x minus 10. Well, that's all. And now check x stationary 5 to d quadrat y dx quadrat, and that will be 2 times 5 minus 10. Oh, it's 0, so this is inflection point. Now you need to find whether it goes like this or it goes like that. Okay, what we do here is to find the coordinates on the left side of x5 and also the right side of x5. So let me set here as 5 1 2 3 4 5 6 7 8. So this is an x, 1 2 3 4 5. So this is my 50. So this is again 10. Oh, okay. So if it is 5 and this is the scale of 1, yeah. Now what happened? So we check that into the original function, into the position of the coordinate. This is step number 3, yeah. We go directly to 3. We know this is the inflection point, so make a short line here, a small line, I mean. Okay, now what is the coordinates on the left of 5? It can be 0, 1, 2, 3, 4, 5. Correct? So what is, I will go to 0 because it's easier for us to find the y. If x is 0, so this is left side of x5. If x is 0, then y will be 1/3 times 0 minus 5 times 0 quadrat plus 25 times 0 plus 10. So you see here 0 0 0, and that is 10. So it is here. Yeah. Well, I think it goes up, but we will test the right side. Right side of x5. What will you take down? We try 6, yeah. x6. Okay. 1/3 6 So power 3 minus 5, 6 quadrat plus 25 times 6 plus 10. Let me see. I'll calculate that first. Okay, so this is 52. So 52 is bigger than 51.67. So this is 51.67. So 52 is kind of goes up, yeah. So this inflection point goes more positive like this. Okay, so this is how you check the inflection point. All right, okay, through the last example here, I hope you will understand about how to find the optimization through the with function with one independent variable. And please go to the next exercises here, yeah, make it, and we'll see that in the class whether you have work on that or not. Okay, see you.